something I just don't know. I can feel it. All right, it's 10 o'clock. Let's get started. Can you hear me? Anyone here? All right.
Yep, we could hear you.
All right, so first of all, the midterm is graded. Overall, it was pretty good, and I am quite pleased. I think that midterm pretty much averages out the first midterm. So for the third midterm, we'll try to go for a level of challenge that kind of averages those two, hit nice sweet spot in the middle. That said, I know it didn't go as well for everyone, so I want to give an option. If things have not been going so well, you don't have to decide right this minute. In fact, we won't discuss it at all in class today. But by next Monday, your option is this. You can decide to not do the remaining new material for the semester, but instead go back and redo things from the first half, from the first two midterms. And you'll have a different set of assignments, and your third midterm and final will even be different. And all you do is just review this material from the first half. And the grade that you could get would be a little bit lower. We'll discuss the grading and logistics of this in a moment. Here's the reason why you should think about it. If you really get down multivariable calculus, linear algebra, and differential equations, you can go pretty far in the rest of our curriculum. If you really truly get those sophomore level math classes down, then the rest of our curriculum is manageable. There are some obvious drawbacks to not learning Fourier transforms, not learning eigenfunction expansions, but there is still a tremendous amount that you can do if you just get sophomore level math. And a lot of the things that people had the biggest problems with on the midterm were things in linear algebra, vector calculus, Taylor series. You know, most of you did fine. So if you want to just stick with what we're doing, you don't have to tell me anything. You don't have to sign anything or inform me of any decision. You just keep right on going. But for those of you who really need to step back and get down the fundamentals, then here's what we'll do. You will not, you'll still turn in the problem set this Friday. You'll still turn in the midterm do-over, but starting next Monday, instead of doing the usual assignments that are up there, I will post alternative assignments. And it'll basically just be to go back and do most of the problems from the end of the chapter in the first several chapters of the book. We'll do a different submission, homework submission, because it's going to be too complicated to have the Blackboard grade book set up with different formulas for different people. So we'll just ignore, for those of you who decide to take me up on this option, we'll just ignore the Blackboard grade book and we'll do everything via a separate channel rather than trying to fit two very different things into one format. Alternative assignments, basically just going back and redoing old chapters, doing almost every problem at the end of those chapters. Alternative midterm and final. But if you're not getting any of the new material, then the maximum possible grade for the semester is a B-, and that's if you completely ace everything. Otherwise, you know, it'd probably be a C something, C plus, C, C minus, whatever. And of course, if you do terribly, well, then you do terribly, and there's no getting around that. But if you decide that all you're going to do is just completely devote all of your time to trying to get down the sophomore level math, I will give you a chance at a C+ or B-. And the reason to take this would be, one, your grade right now is not looking so great, so a C+ or B- is a reach. And two, if you really get this down, the rest of our curriculum is manageable. If you don't, the rest of our curriculum is going to be hell. And for the rest of you who are going ahead with the regular material, I hope you consider this fair to you as well, because, you know, if you take on the challenge of learning the new material, then you should have a chance at a higher grade. If all you decide to do is go back and redo what you really need to get down, well, you should have a chance to pass. It won't be as high of a grade as it could be if you really learn new material. So I'm trying to balance some fairness to both camps and try to make this useful to everyone, because as much as I sometimes rant and get carried away, I will tell you that the single most painful and difficult thing to watch is to watch people flounder at things that the curriculum placed a while ago. And it's not just in the, oh my God, what's wrong with you way. It's in the, what is the point of this? You know, the curriculum, it has a certain pace, and there are things that people will say about the problem with the curriculum having a pace. You know, why is that? Isn't that unfair? Well, there's something to that. But on the other hand, college isn't meant to be forever. You're not meant to be here for 12 years. You're meant to be here for, you know, something closer to 4. So if we're going to learn all of this in some reasonable time, then there's got to be a pace. And because all of this is cumulative, because everything builds on everything else, at some point you've got to say, all right, we assume you've crossed this line, now we go to the next one. And if people haven't actually crossed that line, then it's just very painful to watch. It's just people spinning their wheels. And you could say, oh my God, he's being harsh and judgmental. That's what some would say, but it's not just about being harsh and judgmental. I'm sitting here collecting a paycheck while watching people spin their wheels, knowing that I'm getting paid and they are paying for something that doesn't necessarily make a whole lot of sense. It's just no good for anyone. So I've made the case for it. Here's how this will go down. I am going to, by Friday, post something on Blackboard that will outline the exact requirements. It'll be how many assignments a week, and I won't have all of the remaining assignments done, but I'll have at least one of them. It'll be the assignments, the grading scale. And by Monday, you either submit the next practice assignment or you submit this agreement. That's your choice. Either the practice assignment or an agreement to the alternative. If you submit the practice assignment, you don't have to at any point tell me, Dr. Small, I don't want to do the alternative. You don't have to email me and say, Dr. Small, I just wanted to be sure we're not doing the alternative. The only way you do the alternative grading is if you on Monday, in place of your practice assignment, submit an agreement for the alternative. And then we'll work out something, and that'll be posted on Blackboard in the next few days. Any questions on that before we get back to Fourier stuff?
What do you mean by the rest of the curriculum is like manageable just by the math that we've already learned?
What I mean is that stuff like Fourier series and Legendre polynomials shows up, but it gets covered again, and you don't use that. You use it, but you don't use it as much as you use linear algebra, differential equations, and multivariable calculus. Okay. And you can say, well, if that's really all we need, then why are we doing this? Well, that's not really all you need. That's like the minimum. That's enough to get through. That's not enough to deeply understand all of it. There is no such thing as enough math to do physics, because there's always more math. But if you really get linear algebra, differential equations, and multivariable calculus and vector calculus, you can survive the rest of the curriculum. You won't ace it. There are certain things that you'll be seeing for the first time in the later curriculum, whereas if you stick with this stuff, you'll be seeing these topics for the second time in the rest of the curriculum, but you'll survive. All right. And if you're doing well, I really hope that people who are doing well don't just say, oh, well, I'm going to kick back. Okay. Because you don't need to, and you shouldn't kick back on Fourier transforms if you want a career in the higher realms of physics. But if your main goal right now is survival mode and things just aren't making sense, then let's focus on getting the sophomore level math down. You can say, well, is it fair to give people a passing grade at all for an upper division class for sophomore level math? Well, given that the first two midterms covered things that were at least to some extent a review of what you saw last year, even if done a little more explicitly and more sophisticated notation, that's part of this class. I think it's fair to give a passing grade for that. Other questions? Okay, now let's talk about Fourier. I postponed the problem set because I could tell from the questions I was getting that people were still fairly early into the problem set late last night. So I want everybody right now to go look at the problem set and pick one problem that you want me to go over, and then post your answer in the chat box. And whatever is the most popular is what I will do. I'll do one problem from the problem set. So take a minute, go through the problem set, go into the chat box and tell me which one you want to go over.
Would you do a whole problem or just like a subsection, like part A or part B?
Give me the whole problem and I'll at least go over pieces of the subsections.
All right, cool.
Looks like a close race between 2 and 5. Looks like more people want 5. Okay. So suppose that the function is purely real. Doing the Fourier series of something that problem set 9, number 5. So we got a complex Fourier series. F of x is the sum of Cm e to the I m omega, sorry. E to the I m k x. And let's say that f of x is real. Well, what that means is that the complex conjugate of f star of x equals f of x. So if I just look at pairs of terms, Cm e to the I m k x plus C minus m e to the minus I m k x, that's f of x. So this would be C, so the complex conjugate would be Cm star e to the minus I m k x plus C minus m star e to the I m k Cm star e to the I mkx. And if we equate like terms, here we've got e to the I mkx, e to the I mkx. Equating these means that c minus m star equals cm. And likewise, equating this and this, these are both e to the minus I mkx. That means that c minus m equals cm star. So c minus m and cm are just complex conjugates of each other. Any questions so far?
How come we're dealing with complex numbers even though we stated that f of x is real? Do we only take the real parts of them at the end?
Well, if we state, there's two ways we could do this. One is you could always just write down a Fourier, some arbitrary function, Fourier transform it, and toss the imaginary part in the trash. But if you don't want to do that, if you want to just stipulate that this thing is constructed so that it's real, then you could ask, well, why are we dealing with complex numbers at all? Because I said that we want to build this out of complex exponentials. And the question is, how can you build something out of complex exponentials? If you choose to use complex exponentials as your building blocks, because they're mathematically simple, then how can you add them up to get something real? And the answer is that they better come in pairs that have, they better come in pairs that are complex conjugates of each other. Whenever you add something to its complex conjugate, you just get a real number.
Oh, so, okay, so just because a function is real, it doesn't necessarily mean that we're not going to be working with complex numbers. It just means that the end point, or at least the sum of these components, are real.
Exactly. It's like saying that just because a substance is electrically neutral does not mean that it can't be made out of positive and negative ions.
Okay.
Positive and negative ions and combine them to get something that's electrically neutral. You can take acids and bases and combine them to get something with pH 7. Right? So, and I'm using those analogies deliberately because one thing I've said is that everything we're doing in the class with taking functions and breaking them into pieces is very much like chemistry. There's a periodic table of the 80-something naturally occurring elements, and then the other few dozen man-made elements that any substance can be broken down into. Likewise, these are functions that anything can be broken down into. Now, sometimes it's not at all useful to think about breaking things down into a particular kind of function. You know, we're talking about functions where it's very useful to break things down into sines and cosines. Sometimes it's more useful to break them down into Legendre polynomials or Bessel functions. We'll get to Legendre. We've seen a little bit of Legendre polynomials. When we get to wave equations, we'll talk about why the Legendre polynomials are sometimes more useful and why the Bessel functions are sometimes more useful. Likewise, it's not always helpful to think about a chemical in terms of elements. That might sound like it's completely opposed to everything you ever learned in chemistry. But in biochemistry, you don't normally point to a protein and say, well, this has a whole lot of carbon, hydrogen, oxygen, and nitrogen in it. You point to a protein and you say, this is mostly made out of hydrophobic amino acids, or this part is mostly made out of hydrophilic amino acids, or this other thing has a lot of highly polar or charged amino acids, or basic or acidic amino acids. You know, you break it down on that level. It's just a given that of course it's made out of carbon, hydrogen, oxygen, and nitrogen. But you say what's really important right now is to learn what kind of amino acids is it made out of. And likewise here, sometimes we break functions down into Taylor series. We make them into polynomials because that's the most useful way to look at it. Other times we break functions down into sines and cosines because that's the most useful way to look at it. And sometimes we break them down into other functions entirely because that's the most useful way to look at it. Other questions?
Thank you.
All right, so then what we could ask is, what if our function is not necessarily real? It might be real, might not be real. But what if f of x is even? Then we better have that Cm e to the I m kx plus C minus m e to the minus I m kx is just something times cosine of m kx, right? And then we've got to think about what would it take in order to make the signs go away. And so the way I would think about this is Cm plus C minus m cosine mkx plus ICm sine mkx minus IC minus m sine mkx. And then I'll let you think about what would it take to make the sign go away. So something needs to cancel it. And since we can't gather up Twitter mobs to cancel terms and equations, we instead have to require that those terms in the equation satisfy some sort of identity, which also sounds like something that a Twitter mob would be interested in. But anyway, no, it has to satisfy some sort of relationship involving plus and minus signs and the coefficient with m and the coefficient with minus m. And I think with that, you can figure out where to go and then do something analogous for odd functions. Anything else?
When you say f of x is even, that means that if we plug in like a negative value for x, it'll still give us a positive answer?
Oh, no, not at all. Doesn't at all mean that. Here's an even function. The value over here at minus x is the same as the value over here at plus x. That's an even function.
It basically means that its reflection is equal to itself over the y-axis.
Yep. There's an even function that is sometimes positive and sometimes negative.
Oh, so like negative x and x will give us the same value if the function is even?
Yes.
Okay.
All right. Let's go back into Fourier transforms now. We said last time that any function satisfying a few key conditions can be written in this form. The integral of a of k e to the I kx dk, where a of k is 1 over 2 pi integral from minus infinity to infinity f of x e to the minus I kx dx. And this is basically the inner product of e to I kx with f of x. And remember that in an inner product, one of the functions gets conjugated. Hence, we've got a plus sign here and a minus sign there. And we did a few examples. And one of the examples that we did was e to the minus alpha x squared. if we were to find, let's say that this is f of x, and then a of k would be 1 over 2 pi. I can never remember where I put the 1 over 2 pi. It doesn't really matter. Because people in practice always look for the peak of a spectrum. They're interested in where the peaks and nodes of the spectrum are, not in, I should say almost. It's very rare that people actually care about the specific height of a peak in the spectrum. They care more about where the peak is and if it's higher or lower than some other secondary peak. All right, so we're going to write this as alpha x squared minus 2x ik over 2 alpha plus, sorry, what I'll write is this, plus ik squared over 4 alpha squared minus ik squared over 4 alpha squared. And that is alpha times x minus ik over 2 alpha squared. That's these three terms from computing the square, minus k squared over 4 alpha. So we've got that I need to move this icon. We've got that a of k is 1 over 2 pi integral from minus infinity to infinity. You know, I think I'm going to leave that out. I think I had that before. That is e to the minus alpha times x minus ik over 2 alpha squared, e to the minus k squared over 4 alpha dx. Which is, well, let's see here. We can pull out the e to the minus k squared over 4 alpha because there's nothing in there that depends on x. And we're left with the integral of the square root of pi over alpha. And we found that this gets narrower and higher as we make alpha smaller.
Dr. Small, just some quick clarification.
Yeah.
Where you have alpha in parentheses x squared minus 2x whatever, are you completing the square there?
Yeah.
Okay.
Yeah, we're completing the square. Now, we could, of course, modulate this. And we found before that if we have f of x e to the I k naught x, and we Fourier transform that with e to the minus I k x dx. Well, we get the exact same integral, just replacing k with k naught with k minus k naught. All right, so now a of k will just be e to the minus alpha times k minus k naught squared, oops, sorry, e to the minus k naught squared over 4 alpha, because I just take this expression here and replace k with k minus k naught all over square root of alpha, and there's a square root of pi in there. All right, that's what happens if I multiply the function by e to the I k naught x. And what that means visually is that our function now looks something like this. And if I made alpha smaller, oh wait, and actually it should, if I made alpha smaller, then it might look like that. The key thing is that you could go through several oscillations before you notice a decline, all right? Now, what does a Fourier transform amount to? A of k, the way we would find A of k is we multiply by an oscillating function and integrate. Say that k is roughly k naught. Then we've got something that is almost, we're just going to play with real parts for now. We'll ignore the complications. I'm trying to give you a qualitative idea of why these things, I'm trying to give you an idea of why these things are big, not give you an idea of why does the I go where it goes. We're going to be integrating almost cosine squared. All right. Cosine kx, cosine k naught x is positive for a long time. All right. It's not going to be negative until we've gone for many cycles. You might be thinking, well, wait, cosine kx, that could go negative. Sure, cosine kx could go negative, but then so could cosine k naught x. This might be easier if I switch to Mathematica. All right, so I'm going to plot, I'm going to manipulate a plot. I'm going to manipulate the following plot. Plot cosine of 2 times pi times x times cosine of k times x. X going from, I don't know, minus 10 to 10. And k is going to range from, oops, that should be, k is going to go from, say, pi, we'll say 0.75 times 2 pi to 1.25 times 2 pi. All right, and right now we've got, with k naught is 2 pi in this case. So if I put k naught in the middle, if I make k naught equal to 6.28,
Sorry, the first cosine should be 2 pi x or 2 pi k?
Oh, 2 pi times x, that would explain it. All right. I'm going to make, if I've got that, this is roughly, I make this 6.28. And you look at this and I'm going to change my magnification to 200%. You see how it's all positive, all right? If I say that k is 2 pi, so k naught is 2 pi, k is also 2 pi. You see how everything here is positive. And then I go away a little bit. And eventually that product, first it's negative for just a tiny bit, then it's negative for a while, then it's negative for a long time. But if I'm close, if I'm at like right here, you see how for a long time, it's just barely ever negative. We have to take k off quite a bit before it gets negative, or we have to wait. Either we have to make k very different in order for it to get negative, or we have to go out to really large x values, okay? Now, if I'm multiplying all of this by e to the minus alpha x squared, well, eventually e to the minus alpha x squared goes to 0, or it gets very, very tiny so that its contributions are negligible. So let's further multiply this by e to the minus a times x squared, and we'll make a manipulable. A can go from like 0.1 to 5. And we're going to make our plot range always go to 1 so that we can see what's going on. Oh. All right, as I bring k into resonance, here k is around 2 pi. It's not exactly there, but it's close. And by the time things start to go negative, we can barely even see it. And you know what? Let's make this 0.01 to 1, just to make it a lot more clear. All right, by the time things could even begin to get negative, it's practically died off. And if I made alpha still larger, it's died off even more. What I want you to take away, here's what I want you to take away. If I've got k very close to k naught, I never see any negative contributions to that Fourier integral. And furthermore, the smaller alpha is, the farther out I could go and still get positive contributions. So if alpha is really small and I can go really far out and get positive contributions, then I could get a massive value for that integral, right? I could get a really large integral because I just keep adding up positive things. I can go further and further out and add up more positive things. I have to go really far out before anything goes to 0. So now let's take the limit that alpha goes to 0. All right, let's take this out to 0.1. Again, I'll make this right there. All right, I'm going to put this right on resonance. I can hit a whole lot of cycles. This could effectively be at resonance. This could be infinity because alpha is 0. So I could just go out. If alpha is 0, I'll be integrating cosine squared from minus infinity to infinity. And cosine squared is always positive, oscillating between 0 and 1. So the integral of cosine squared from minus infinity to infinity is infinity. But if I go off resonance, and I plot it long enough, I just go a little bit off resonance. I'm keeping that at 0. I go off resonance. All right, here I am basically on resonance. I just go a little bit off resonance and boom, that integral becomes 0 because I got all these positive contributions here and I've got negative contributions there. And if I go a little bit further off, I'm going to get positive contributions here and negative contributions there. So you see how if alpha is 0, or if alpha goes to 0, and the limit that alpha goes to 0, when I'm right on resonance, when k equals k naught, I get infinity. And as soon as k is different from k naught, I get 0. That's the delta function. Questions?
What kind of practical uses are there for integrating this cosine squared?
Two very different answers. One is that the delta function shows up all over the place in the theory of signal processing, which we're going to do a little bit of next week. The other thing is that the delta function is essentially the absorption spectrum of a long-lived atomic state, right? Anytime you look at an emission spectrum or an absorption spectrum, if you have a really narrow emission or absorption spectrum, what that means is that at one particular frequency, you get an incredibly strong response. And then as soon as you go away from that frequency, you get no response. So let me share my other device so I can draw again. Why is it not working? So a delta function has a peak at infinity has a peak equal to infinity, 0 elsewhere. And the integral of delta of x dx equals 1. And really, it looks like this. This is the delta function. It is an infinite spike at the origin. Here's delta of x minus x naught. An infinite spike right there at x naught. And really, I could integrate the integral from x1 to x2 of delta of x dx equals 1 if x2 is greater than x naught and x1 is less than x naught, right? If it's in that range. So we don't actually have to integrate from minus infinity to infinity. It's customary to write that way. And you use this to model any spike in a spectrum that is infinitely small. So now we could think of the Fourier transform of e to the I k naught x as the Fourier transform of e to the minus alpha x squared e to the I k naught x in the limit alpha goes to 0. All right, so if I want a Fourier transform e to the I k naught x, that's how I think of it. I think of Fourier transforming e to the I k naught x as really, since I can't, like if I try to Fourier transform e to the I k naught x, the integral from x equals minus infinity to infinity of e to the I, e to the minus I, k minus k naught x dx. If I try to think about this in all the notions that mathematicians normally want us to use, then I'm integrating this. And this integral doesn't actually have a well-defined limit, because depending on my starting and end points, I can get to that integral, goes anywhere from -1 to -1 over delta k to +1 over delta k, all right? It's really not a well-defined integral. But I know that if I take the limit in a certain very particular way that physicists favor and math professors cry over, I get 0. And I also know that the integral from minus infinity to infinity of 1 dx is infinity, which also makes math professors cry. But physicists just do this anyway. All right, so the delta function is the Fourier transform of a sinusoidal function. And the way we normally think of it is that it's the limit of the Fourier transform of this thing, because this thing has a well-behaved Fourier transform. This thing has a Fourier transform that doesn't make math professors cry. And since some of my best friends are math professors, I don't necessarily want to make them cry. So I could think of it that way. Physically, what I think of it as, the natural universe has no truly pure frequencies. In this universe, there are no truly pure signals. Even a tuning fork actually has a very slight mix of signals in it. Even what you think of as the purest atomic emission spectrum has a little bit of width in it. So there are no true delta functions in nature to the best of our knowledge, but it's the limit of something that is very, very pure, so pure that I can model it as a complex exponential multiplied by a Gaussian that is very, very wide. Questions?
This is more of just clarification on your handwriting. So Fourier transform of
E to the I k
naught x.
Yeah.
Okay, and then
I'll rewrite
right
that.
below that. And then right below that, you have e to the minus alpha x squared, and then e to the I k naught x.
X, yeah.
Okay.
In the limit, alpha goes to 0. Fourier transform has a number of properties. If I take the integral f of x delta of x minus x naught dx, I get f of x naught, right? And again, the way you could think of that, if you don't really want to think of multiplying something by a single infinite spike, is taking a very narrow and tall Gaussian we'll say that the area under that curve is 1. And here's f of x. Here's our Gaussian. F changes slowly in there. And because f changes slowly in there, we can approximate f as constant. You might say, well, that's not a very good approximation. I say, well, I can make it a better approximation as I make that Gaussian function narrower and narrower until eventually it's a very good approximation. Then I've got a function with area 1 multiplied by a constant. The integral is f of x naught. How about this? What if I do f of x, the integral of f of x from minus infinity to infinity, delta of m, where m is just some number, how do you think we do that a 1? Well, we don't know how to do the integral of delta of m times x, but we know how to we know how to do this integral. So let's do a u substitution. U equals m times x minus x naught. So then u over m equals x minus x naught. X equals u over m plus x naught. Dx equals 1 over m du. And so what I've got is the integral from minus infinity to infinity f of u over m plus x naught delta of u du over m. And I know how to do the integral of something multiplied by a delta function. I know how to do this integral here. This is just going to be f of 0 over m plus x naught, or 1 over m f of x naught. Any questions? Okay, I said that the Fourier transform of e to the I k naught x is delta of k minus k naught. So how are we going to find the Fourier transform of cosine k naught x? Any ideas? Do we know how to write cosine of k naught x in terms of functions whose Fourier transforms we've already discussed?
Can't you make it the exponential definition?
Yep. It's got to be the Fourier transform of e to the I k naught x plus e to the minus I k naught x over 2. And the Fourier transform is a linear operation, meaning that if we've got, meaning that the Fourier transform of C1 F1 of x plus C2 F2 of x is equal to C1 A1 of k plus C2 A2 of k, where A1 of k is the Fourier transform of F1 and A2 of k is the Fourier transform of F2. That's just a property of them. It comes from the fact that the integration is linear and our integrand is a linear, our integrand is linear in the function that we're working on. The Fourier transform is an integral. Integration is a linear operation, meaning that if you add up two functions and integrate their sum, that's the same as the sum of the integrals of the original functions. So if the Fourier transform is linear, then the Fourier transform of this has to be 1/2 delta of k minus k naught plus 1/2 delta of k plus k naught. So we can have a function whose Fourier transform is a set of delta functions at different positions. And we don't have to just have 2 delta functions. Here's a function that shows up all the time. Shows up in the theory of diffraction gratings. It's just a bunch of evenly spaced delta functions. And this is sometimes called the Dirac fence, because delta of x is often called the Dirac delta function. Paul Dirac did a lot of important work in the early days of quantum mechanics. He extended quantum mechanics to include the theory of special relativity. If you're thinking, wait, I thought nobody's resolved relativity in quantum mechanics. Nobody's fully resolved general relativity in quantum mechanics, but special relativity in quantum mechanics was resolved very early on by Paul Dirac. Paul Dirac also contributed something called Dirac notation, which you'll use all the time next year. And he did a lot of work on the properties of the delta function. We call it the Dirac delta function as a way of reminding mathematicians that it was the most mathematically savvy of physicists who said the delta function is okay to use. So take it up with Dirac. And the mathematicians call it the Dirac delta function as a way of saying, hey, look, this was a physicist's idea, not a mathematician's idea. Because the delta function is not something that mathematicians look upon favorably. So this Dirac delta fence is denoted with this symbol. This is the Cyrillic letter Sha. It's called Sha because, well, look, this letter looks a lot like the function up there. And this is the letter in Russian that makes the sh sound. And it's just a sum from n equals minus infinity to n equals infinity of delta of x minus NA, where A is the spacing of these. And it shows up a lot in the theory of diffraction gratings. It shows up in the theory of waves in periodic systems. It's one of those things worth knowing about. I'll give you a homework problem on it in the next set. What are some other things I want to spend time on? Okay, the delta function violates one of the conditions. Delta function is the only function we're going to deal with that violates the rules. There's something called the Dirichlet conditions. The Fourier transform works if, one, f of x, a of k are square integrable, meaning that the integral from minus infinity to infinity of absolute value of f of x squared dx exists, and the integral from minus infinity to infinity of a of k squared dk exists. 2, F and A are piecewise continuous, and 3, F and A are bounded above and below. The delta function violates that, but basically the delta function is our way of treating things that we know must in nature be very, very narrow, so narrow that the details don't matter. And for many situations, say the width of an atomic transition line doesn't matter, even though those widths are just about always measurable. They're always measurable in principle. Sometimes they're difficult to measure in practice, but those widths are always measurable. The electron is a thing that on some level, I think many people suspect probably has some kind of size or structure. No one's ever experimentally found evidence for a structure to it, but I think many people would speculate that there might be structure to the electron somewhere between the smallest length scale we've ever probed and the Planck scale of quantum gravity. That's a speculation. Nobody knows for sure. Some people speculate on that, but we know that in every experiment we've ever done, the electron behaves as something with a size so small we can't measure it. So we treat it with a delta function, but if you prefer, we could just always say treat it as a Gaussian with a really, 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 really tiny width, so tiny that any other function you're ever going to work with is constant across the size of the electron. That's the way we think of the delta function. Even though it violates this condition for Fourier transforms to work, it's a model for things that are so tiny that we can neglect their details. And when in doubt, we just treat it as a very narrow Gaussian and integrate that. I want to give you a few other properties of the Fourier transform, and then go to something kind of cool. We illustrated this by example last time. What did we find if I shift a function? If I shift a function over, what did we find out last time? What happened to the Fourier transform when we shifted the function?
It modulated the Fourier transform.
Yep, it modulated the Fourier transform or multiplied it by e to the I k something. Let's prove that. The integral from minus infinity to infinity of f of x plus delta x e to the I k x dx. So I could do a u substitution. Du is dx, but x is u minus, oh, and that should be, sorry, that should be a minus sign, u minus delta x. So I could rewrite all of this as the integral from minus infinity to infinity of f of u e to the minus I k u plus I k delta x dx is e to the I k delta x integral from minus infinity to infinity f of u e to the minus I k u. Looks to me like this is just the Fourier transform of f multiplied by this. That's an important property. And the converse also holds. Looks exactly like the Fourier transform, except k has been shifted. So if you shift the function, you modulate the transform. If you modulate the function, you shift the transform. Now here's something. What if we rescale the function? What if we multiply x by some constant? So I want to Fourier transform that, right? If I multiply x by some constant, that means that something that before would happen at a large value of x, something that before, if s was say 10, something before that would happen when x equals 1 now happens when x is 0.1. F of 10 times 0.1 equals f of 1, i.e. a feature at x equals 1 gets shifted to x equals 0.1. So this is a way of rescaling the horizontal axis. And likewise, if s was less than 1, the opposite happens. So this is a way of rescaling functions. And it turns out that there's a nice predictable thing that happens there. The Fourier transform would be the integral from -infinity to infinity, f of s x, blah, e to the minus I kx dx, but I can do a u substitution. X equals u over s. Dx equals du over s. And so this becomes the integral from -infinity to infinity, f of u, e to the minus I k over s times u du. And this is equal to a of k over u. So if I shift all of the features in my function to short length scales, I shift all of the features in my Fourier transform to large k values. And conversely, if I shift all of the features in my function to long length scales, I shift all of the features in my Fourier transform to small k values. So whatever I do to x, the opposite happens to k. And there's two ways to think about it. One is in terms of the uncertainty principle that we've been illustrating again and again. To derive the uncertainty principle, I don't know, maybe we'll do that in a week or two. I'm not sure yet. Deriving it is kind of a mess. Illustrating it is easy. The other way to think about it is that small k values have very long wavelengths. There are oscillations with very long wavelengths. Large k values are oscillations with short wavelengths. So anything that shifts my features to small x means short wavelengths or large k values. Anything that shifts to small length scales that emphasizes small lambda emphasizes big K, and vice versa. Questions? Let's talk about derivatives. F of x is 1 over 2 pi integral from minus infinity to infinity a of k e, sorry, that should be you tell me, if I want to take the derivative of f, where's x in this expression? Where is x on the right side?
In the exponent of e.
It's the only place that x shows up. Only place I can see it. So I take the derivative, I just get I k a of k e to the I k x dk. So this is the Fourier transform of df dx. And this should remind you a lot of something that I had on a follow-up assignment and then that I had you do on the midterm, where we kept finding that for waves, for complex exponential waves, the derivative of that wave could be obtained by, in the case of a divergence, dotting k with the wave, and the curl could be obtained by crossing k with the wave. So del dot a e to the I k dot r was I k dot a e to the I k dot r, and del cross a e to the I k dot r was I k cross a e to the I k dot r. So if I just had one spatial frequency, one kind of wave, and I wanted to take a derivative, then that derivative just meant doing some multiplication operation with ik. Well, now I'm making something out of not one wave, but an infinite number of waves. And for each of those waves, I just multiply by ik. And right now we're doing one dimensional. When we get to higher dimensions, there are extensions. But again, it's the same idea over and over. So if you've got a function, the Fourier transform of its derivative is ik times that Fourier times the Fourier transform of the original function. Conversely, if you've got some complicated Fourier transform and you're not sure how to invert it, you're not sure what function this is a Fourier transform of, ask yourself this. I might not know what that function is, but what if, is this ik times something that I do know the Fourier transform of, or the inverse Fourier transform of? Is this ik times some Fourier transform that looks familiar to me? Oftentimes the answer will be yes. Questions? All right. I'm not going to try to introduce a new topic in the next 30 seconds. On Friday, you'll have an activity where you take a bunch of Fourier transforms, do a bunch of plotting, and see the uncertainty principle illustrated again and again. Use a lot of Mathematica there. And then on Monday, I'll do Parseval's theorem generalized to Fourier transforms, and then we will start convolution and a few ideas from signal processing, which is a chapter in the Fourier Transforms book. Remember that the midterm do-over and the problem set are due on Friday, and then the next problem set will be shorter to compensate for the delay. Have a good day.
Thank you, Professor.
Thank you, Dr.
Thank you,
Small.
Dr. Small.
Hey,
You're
Dr. Small.
welcome. Bye.
Hey, Dr. Small.
Yeah,
If we got 100 on the midterm, can we resubmit the same document?
I thought I emailed those who got 100 on the midterm.
Oh, you may have. I just may have not checked.